So creating foundation model is very hard. So first thing that you need is a lot of electricity. So that's the nuclear power reactor over there. There is a reason why everybody is talking about nuclear, is because GPUs and the training process is extremely energy intensive. So when we were training, one of you was making a comment like, did you guys find a nuclear power reactor? And where is it in Montreal? So we do our R&D in Montreal, yes, but the training actually, we did it in Finland. So Finland happens to have a ton of hydro power, and they're sitting on a pretty big surplus of hydroelectricity that they sell in Europe. So our training for the foundation model is actually happening in Finland on GPUs. It does require a lot of money as well, not just the electricity, but the money. The money goes to buy data sets, it goes to buy the expertise. So we have an awesome AI research team, and it goes to pay for the GPUs and the electricity and so on. So it's a pretty lengthy process as well. So what's interesting about the training process is that once you train the model, so you load the model into the training process, and you basically have to go away and make yourself some tea, because the process is going to take it a month. So it's basically training the model, and the training process is about a month. That's for our biggest model, which is about 40 billion parameters. The smaller one takes several days, but that one is 7 billion parameters. So there is kind of the scale on the size of different models that you have. The training process itself is actually elegantly simple, and this is something that hopefully you would be able to use in your organizations when people say the AI is unexplainable, it's a black box, etc. Number one, it's not a black box because you can see exactly what's inside the training data set if you're working with a vendor that would actually tell you what's inside the training data set. But they can also tell you how they've trained it, and so this is how all the foundation models are trained. And the reason I say that it's elegantly simple is because this is how you would actually learn a foreign language. So for those of you who learned English, you probably would remember that one of the exercises that you have to do when you're learning English is fill in the blank. So what typically would happen is in the textbook, the exercise would be, here is a sentence and there is a word missing, and you have to guess which word is missing. The way you would guess it as a human is based on the words on the either side of the sentence. So in this particular example, I can guess that the word that's missing is the word go in the first sentence. In a second sentence, I can guess that the word that's missing is bank, and so on. So you would do this as a human, and what the key innovation that we came up with, and we as in humanity, okay, in 2017 was this, which is what would happen if we took Wikipedia, billions of sentences, and we randomly deleted 20% of the words. And then we fed the data set into a computer model, and we forced the computer to guess which words got deleted. And you would do this over and over again, millions of times, until it's able to guess which words got deleted with uncanny precision. Once you've done that, it would actually be able to understand the relationship between the different words. And here's an example of the relationships. So if you look at the first sentence, it says, I need to go to the bank to deposit this check. The two words that are highlighted in green are the two most important words that are driving the meaning of that sentence. It's the word deposit that defines the meaning of the word bank. In a second case, you've got a sentence that says, the bank of clouds in the sky is a sign that it may rain soon. Clouds is defining the meaning of the word bank. In the third one, the word river is defining the meaning of the word bank. The spelling of the word did not change. It's the same old bank. But the meaning of the word changes based on which word is next to it. And the process of deletion of words, surprisingly, turns out, gives the computers this uncanny ability to relate words in English to each other in myriad of different ways that humans typically can't. Like, we intuitively get it when we're learning the language, but that's how, and it organizes the information in our brain, but it's able to see these patterns in ways that human brain cannot. So this process is what allows AI to understand human language. However, AI does not see letters the same way that we would see letters. What it sees is the matrix. The matrix actually is one of our customers who was explaining that. So they're based out of London, and they had to make an explanation to the regulator how AI works. And it was that person who came up with this idea that maybe we should explain it as AI sees the matrix. So here's an example, okay? Let's invent a process by which we're going to convert letters into numbers. Okay, and we're going to take the alphabet, and A is going to be represented by number 1, B is going to be represented by number 2, C is going to be represented by number 3, and so on. So if I wanted to spell the word bad using numbers, I would use 214. And if I wanted to spell need to buy it before the announcement, this is what that encoding would be, right? So all I've done is just taken each letter in that sentence and replaced it with a number. Make sense with me? All right. So what would happen if I took this sentence and put it inside the brain of AI, and I wanted to really see it, like how is it represented inside the brain of AI? This is what you would see. This is real representation of that sentence inside the smallest model called BERT. So BERT is 100 million parameters. It's the first model that was using the transformer architecture. It was invented in 2017 by Google. All of Google search now runs on BERT. They probably would have upgraded ever since then, but this is the way it sees that same sentence. That BERT representation, if I count the numbers, like how many numbers are there in that matrix, inside that matrix, that's 9,200 characters. So the small sentence, need to buy it before the announcement, became 9,000 numbers. Okay? So if I did the same thing with Behavox LLM, you would get to 51,000 numbers. So that one small sentence becomes 51,000. You can now start thinking about, well, oh my gosh, if I'm going to take that one sentence and I'm going to put it into this number representation that is into tens of thousands of characters, it's going to be very heavy to store, very expensive to store. And that is exactly why AI is so astonishingly expensive to run, and why NVIDIA is a $3 trillion company, is because to just copy and paste 50,000 characters is already an expensive operation. To do something even more complex is going to require you a lot more compute. So the world is going to be very quickly running out of electricity and very quickly running out of GPUs. This is a new piece of information. There's something called dimensions. And when AI interprets information, so before I get to dimensions, for those of you who are math whizzes, you will understand when I talk about dimensions and matrix and equations. For those of you who are not, this is a matrix, so it has a whole bunch of numbers in it. And the size of this matrix is determined by this notion called dimensions. Okay, so more dimensions means thousands of numbers. Less dimensions, less numbers. Okay, makes sense? With me, right? Dimensions is the most important thing that determines the quality of the model. And here's an example. We've got a red object, and we need to describe it. We can describe it using color, we can describe it using size, we can describe it using material, we can describe it using shape, and so on. Now, each one of those things that I just mentioned is a dimension. So each one of those characteristics. And to get to 51,000, you're essentially saying that is a representation that has a number of different dimensions. So Behavox LLM, for example, has 10 times, roughly what, 5 times more dimensions than BERT. So then there was another question that said, well, why do we bother with these matrices and numbers, and like, why do we want to go into that nth level of detail? Here's why. Could you use prompt engineering to generate alerts? Yes, you could. However, prompts change. Why do they change? Because depending on how AI feels at any given moment in time, and I said feels intentionally, it will produce a different response to you. So one day you go in and you say, let's trade something before the announcement. And it's gonna say, it's a true positive, it's illegal, shouldn't be doing it. Next day you ask the same question and it will give you a different response. Why? Because there is, in the chat interface, there is something called temperature, and that literally is the feeling. It's a random variable that was introduced into the way the chat model works. And as a result of it, every prompt and every response is different. And obviously, if you're deploying our solution as a compliance surveillance solution that is supposed to be catching bad actors, I cannot go to you and say, well, one day it will feel okay and it will catch somebody. Another day it may not feel okay and it will not catch somebody. And I cannot tell you how to control that feeling. It's regulated by random formula. It's randomness. So that definitely is not going to fly. So how do we do it? Well, so under the bonnet, we're actually using our LLM as a number generator. We're actually not using it to generate alerts. So what would happen is that you would take your compliance policy, or you would take true positives, the knowledge base, and you would put it into a number representation like shown over there. Admittedly, it's not going to be a few numbers like it's shown over there. It's going to be billions of numbers. And then every phrase that goes in, every question that goes in also gets converted into a number representation by the same model. Now that we have number representations on one side and number representation on the other side, it's very easy to do a VLOOKUP function. That's for those of you who are non-technical. So you're essentially doing a VLOOKUP of these numbers inside the data set over there. Now, this is actually not a VLOOKUP. It's actually more sophisticated. It's a regression algorithm that would actually be able to compare that. But if you were explaining this to a regulator, like how does it actually work? Well, this is how it would work if you're using something like a Behavox LLM. So we're not using prompting. Hopefully you're still with me, right? So, and obviously, the bigger the number representation, the more accurate is the VLOOKUP. And this is where the challenge comes in, which is to get to a big number representation, you need to have more dimensions. More dimensions means that the number representation is gigantic. And if it's a big number representation, like 51,000 characters, it becomes expensive solution. And for those of you who are compliant, we totally feel your pain when you have to go and ask for budget. So we really work hard on making sure that it's affordable. And that's the other reason why we decided to invest into our own AI, is because we want to give you control, visibility into the training data sets, but we also want to make sure that you're able to run our model in production affordably. And the only way to achieve that is if we control the architecture of the model itself.